the idea that you can use a trivial code to obtain the most efficient possible representation is usually false. So for instance, in English, just in English text, how many symbols do we have? Well, we've got 26 letters plus punctuation. Even if we just consider the 26 letters, which letter is the most common? Does anybody know?
E.
It's E. If we consider 26 letters plus punctuation, what's the most common symbol?
Space.
Space. So even in that case, there are more common symbols and less common symbols. So it's very, it's a very poor assumption to assume that every possible message that you want to send is equally probable. One other thing, in the textbook, if you read through the textbook, you'll come across a case where they look at not just individual letters, but they actually start grouping letters. So it turns out that if you group letters together, it turns out there are pairs of letters that are particularly common, even more so than just the individual letters themselves. So if you start looking for extra structure, you can generally find it. Okay, so here's a more complicated example. So what we're going to do is we're going to say we have a database for representing grades. So let's say we have a very large class and we have a database in which we want to store the grades of everyone who's taking this class. So the possible messages are these, are all the possible letter grades. So at York, all the possible letter grades are A+, B+, B, C+, C, D, and F. I'm going to group E. I think it's possible to get an E, but I'm going to group E and F together. So those are all of the possible letter grades that you can get. But obviously, these events are not equally probable. In particular, let's say it makes sense that the average person would get a C. So let's let C's have probability 1/2. C plus has probability 1/4. B can have probability 1/8. D can have probability 1/16. And all the rest, A+, A, B+, and F, have probability 1/64. So this is a fairly harsh class. Not very many people are getting A's. But on the other hand, not very many people are getting F's. So just about everybody's getting a C. Okay, so how many symbols do I have here? What's cardinality of M? It is 8. Let's say I want to represent this in binary. So X, my set of allowed symbols, is binary. Cardinality of X is 2. So in the trivial case, how many bits do I need? I need 3, obviously. So 3 bits. 3 bits for the trivial representation. Okay. Instead of that, so let's have 2 competing representations. So here's the grade. Here's representation 1, which will be the trivial representation, and representation representation 2, which will be something different. So, my grades, I'm going to list in order of probability of occurrence. So the most probable is C, then C+. I'll write the probabilities over here. 1/2, 1/4, B, probably 1/8, D, probably 1/16, and then A plus, A, B plus, and F is probably 1/64 each. So, okay, representation 1 is the trivial representation, so 3 bits each. So let's say C 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So for representation 1, what's the average length?
3.
Obviously it's 3. So what I do when I calculate the average length is I take the sum over all the possible letters, so M in the set, M in the message set, of the length of the representation of M times the probability of M. So in this case, the lengths are all the same, so I get 3 times the sum over M of probability of M, and what's the sum over the probability of all possibilities? Obviously it's just 1, so that's 3. Okay, now here's my second representation, and I'm going to use the philosophy that we talked about a second ago, and I'm going to assign to more likely events, I'm going to assign shorter representations. So for the C, let's just represent that with a 0. For the C plus, 1, 0. For the B, 1, 1, 0. For the D, 1, 1, 1, 0. For the A plus, 1, 1, 1, 1, 0, 0. For the A, 1, 1, 1, 1, 0, 1. For the B plus, 1, 1, 1, 1, 1, 0. And for the F, 1, 1, 1, 1, 1, 1. Okay, I will deal with the problem of whether this can be uniquely decoded in a second, but for now let's just assume that it can. What's the average length of representation 2? Well, what are the lengths? Here I have 1, 2, 3, 4, 6, 6, 6, 6. So the average length is equal to the sum of the lengths times the probabilities, which is equal to 1 times 1/2 plus 2 times 1/4 plus 3 times 1/8 plus 4 times 1/16 plus, and there's 4 of these, 4 times 6 times 1/64. So what do we end up with? We have 1/2 plus 1/2 plus 3/8 plus 4/16 is 1/4 plus 4/64 is 1/16. 6/1/16 is 3/8. So this is 1/2 plus 1/2 is 1. 3/8 plus 3/8 is 6/8, which is 3/4, plus 1/4 is 1. So this is 1, and these 3 are 1, so that is a total of 2.